the IETF. So we follow the IPR policies of the IETF. Actually, IETF follows the IETF IPR disclosure rules. If you have disclosure in your proposal, you are responsible to disclose that according to the IETF request. As early as possible, that says in a period measured in days or weeks, not months. Before we start the meeting, we'll hand out the blue sheets. Make sure you sign that. If you want to leave the room earlier, sign the blue sheets before you leave. We need a chip scriber and a minutes taker. Anybody volunteer for that? Minutes taker? We have to have a minutes taker to. Oh, Bing. Thanks, Bing. If somebody happen in the job room, could you please just tell the remote participant where the page is? We probably, as far as I know, at least 2 remote participation there. All the slides I already uploaded. It could be downloaded from the proceeding or the material site of IETF. We have the mailing list NMLRG at IETF.org. You can subscribe it through the link I provide here. The charter could be found in the data tracker of IETF. We also maintain a wiki page under the IETF tools. For now, this proposed research group is chaired by me, Xin Jiang, and Brian Cameter. This is Brian Cameter. No, joke. Yeah, and this is Suresh Hashman. Thanks for him because Brian cannot be here, so he's kindly agreed to sit in to help. Thanks, Suresh. This is our meeting agenda for today. First, I will give a very brief introduction to machine learning and its potential usage in network area. Also explain a little bit on the proposed NMLRG and what we are expected to do. Then that's the multi-dimensional aggregation for DNS monitoring by Jerome. After that, that's applying machine learning to software-defined networks, introduce the use case and ongoing experimental results by Albert. The 5th topic was our last-minute modification. It's machine learning in spam filter. I only added that yesterday, but actually it was our first planned topic. By some misunderstanding between John and me, I didn't include that in our charter, but since we already talking about very earlier, so I make an exemption there to add it in. After that, it's the autonomic network configuration using machine learning mechanism made by Shu Fan. The last topic is the research on the network fault analysis based on the machine learning made by Haibin. Haibin, is there? All right, sorry. So anybody has anything to say regarding to the agenda? Okay. If not, then we can move to our first topic. Okay. Okay, this is a very brief introduction to machine learning. Actually, I already submit a draft, very primary draft to the NMLRG. Hopefully, it will serve as a container for our future use case study. For now, it's including some background knowledge for machine learning and the proposed charter for our NMLRG meeting. Next page. Okay, first of all, why we are doing this NMLRG? The network and the network problems already become more and more complicated. There are many varieties of network, and the network is keeping dynamically changing. So that means our traditional way by designing the programming or the fixed programming, we cannot continue when the tasks become too complicated. So we are looking for new mechanisms that can adapt to various and dynamic environment by itself. We are also looking for the autonomic mechanism to replace human operator, because the human operator could not, expand to handle those complicated issues, and also the human operating take time to respond. Sometimes, the problem may come very quick and may go very quick. So the human response time may not be enough. Actually, we may also, target to replace the human programming. This could benefit to, reduce the programming cycle in the developing stage. On our side, the machine learning itself was motivated by the tasks that are extremely difficult to program by hand. By applying machine learning, what we can get is robustly solve the complicated tasks. This would rely on real-world data instead of pure iteration. Hopefully, this can be able to adapt to the new situations. Then, it can develop by itself when the time goes on. Next page. As we said, the machine learning can learn from the historic data. It makes the production or decisions rather than following statistical program instruction. By doing so, they can dynamically adapt to a changing situation and enhance themselves and its intelligence by learning from the new data. So the environment developed, environment changed. The new data from environment will become the new input and change the intelligence of machine learning. For now, they have been successfully in many areas, image analysis, language recognition, conversation simulation, and many other applications. But in the network area, we haven't heard a lot of successful story yet. We know there are many ongoing research, but they are not mature yet. So this is the time we can, come together to speak and to communication, to the research together. On the left figure, that's what we do for now. That's a traditional way for solve any tasks in computing way. We have the program, which is mainly based on the if-else. That means, we the developers, abstract their human knowledge and try to express them into the if-else program, fix them in the computer program. Then the computing process can take the task which has the accurate data that describes the target. This data has to match at least one of the design, pre-design conditions. Otherwise, it may fail or may fall into the else condition. But the else probably, developing in some very generic way may not match the exactly the situation. That means if the situation become more complicated or develop some new situation, the fixed program may fail. Also, if you want to cover all those corner cases, your program become more and more bigger and bigger. We say our coding data, coding lines for the router, almost double in 2 years. So that will be continued if we still doing the if-else way. The right figure is what we have for the machine learning. The input is the data either from historical data or the environment testing measurement. Those data may already have some historical knowledge which embedded when the first time the human administrator or human planner to set up the network or set up the environment. Then for machine learning, we have the designed machine learning patterns or and algorithms. We need to carefully design a learning path to learn this, the target. The learned result is some rules. They may not be right down. They may not match the human knowledge, but there are rules. The computing could take for the further process. Then when the real target come, it could come in the approximate way with the data. The computer can take those data, match them. It's not need to be perfect match, so that the machine learning could be adopted by itself. Apply those learned rules, then give out the target result. This mechanism could be, more generic to adopt different tasks at different environment. Next page. A little bit introduction to machine learning itself. The machine learning mechanisms are typically classified into 3 broad categories, depending on the nature of the learning signal or feedback availability. The supervised learning, which most of data are labeled, and the unsupervised learning is more freedom. The machine learning process can decide the form of result by itself. Reinforcement learning is mainly takes the feedback from the environment. There's also semi-supervised learning between supervised and unsupervised. For the approach and algorithms, there are a few basic mechanisms. They can be mixed together to complicated tasks. At least some of them, most frequently used. Classification, clustering, regression, anomaly detection, density estimation, dimensionality reduction, decision tree learning, associated rule learning, artificial neural networks, reinforcement learning, similarity and metric learning, also representation learning. There are more. This is not a full list. And in the future, maybe new algorithm and new approaches may developed. But this is basically the toolbox we can use in machine learning. Expected. What's the preconditions we can use apply the machine learning approaches? First, it's the data. Although machine learning is different from big data or data mining, machine learning does need data. However, machine learning can be applied with small set of data. That depends on the quality of data and maybe combined with some prior knowledge from a human being. Or it can dynamically feedback from the environment. The quality of data actually decides the efficiency and accuracy of machine learning result. And there is no generic machine learning mechanism that could suitable for all or most of use cases. Although we said machine learning has the ability to adopt by itself, but for different use cases, the learning paths, the way to handle or the way to combine with prior knowledge is different. So for each use case, the developer needs to design a specific learning path, which may combine with multiple approaches or algorithms together. So in machine learning design, the feature design and the learning path design are the key factors which will influence the usability of the result largely expected. The limitation. So far, the machine learning mechanism does not perform very well for the aggregate result. But now, in most of successful cases, it is used as an assistant analysis tool. Many of them request, the human operator or the human administrator to further confirm that, or they can be used only in the fault-tolerant environment. For example, if the machine learning in the conversation translation, may developing some sentence in, very strange way, but still, because it makes the basic translation, so let's still be able to understand by the human being, even the tongues may be strange. And the quality requirements on data is also an ongoing research target. There are many aspects to measure the quality. Until we, for the very specific use cases, we are not sure, what is the quality we request for that use case. And there are many scenarios, maybe most important element may not be measurable or quantifiable. That means even we have many data, they do bring the impact to the result. But if the most significant element is not included, that means whatever the machine learning solution we designed, that could be failed if any one of the important elements which is not data presented failed or changed. Next picture. There are many more considerations we are still thinking and keep on going research. To achieve autonomic design or minimize the human intervention, there should be an evaluation system for the result of machine learning mechanism. That could, for now, many of the successful use cases actually use the human being, use the human experience to do that evaluation. So that's why earlier we said the human confirmation may be still, very important. But if we want to do the autonomic design or, make the system running with minimal human operation, so our autonomic evaluation system must be there. The evaluation system and machine learning mechanism together could compose a closed decision loop for the autonomic design. The next consideration is the prior knowledge. For many use cases, if more prior knowledge are applied, that means the result could be more accurate and the computing process could be much more efficient. But the problem is the more priority knowledge applied, the less universal the solution could be. And that may also, bring impact to the adaptability there for the machine learning. Because if some of this prior knowledge applied is not, happen, or maybe different scenario, different situation in the new environment, the design machine learning process may be, failed. That's the limitation of the adaptability of machine learning. And for now, for most of use cases, human interaction is still very important to improve the usability of the result. So maybe for the short term, the best way is still, involve human confirmation or human intervention in the solution. But by applying machine learning, it can definitely reduce the human intervention in the operation process. The machine learning could be combined with traditional mechanisms. That means if there are very sure conditions or very sure choices between the along the situations, they could be solved through using the traditional mechanism. Only introduce the machine learning when the situation could change very fast and dynamically change. Then together, it may be the best efficiency way. Incremental mining, that means the designed mechanism from the historical data could also, get the input from the dynamical environment, and those data together maybe change the way the machine learning applied. That the new data will be weighted over the historical data, but they both impact to how the result may be. And developing in the time, the behavior of machine learning process could be very different. The mechanism itself could self-iterative optimization by itself during the time. That depends on the very quality new data coming, and the mechanism could adapt with the environment. It could become better and better. But that may introduce another issue is if one machine learning mechanism sitting there on a device and has a very adaptive with the environment, but that device is broke down. How we transfer that knowledge and the result to some new devices, how that knowledge transferred. If we just replace the broke down devices with that brand new devices, that means the training process may have to repeat, and there may be a period the new devices may be less performant than the old one, because the old one already well trained. Okay, next page. Okay, the potential usage in network area. Machine learning can be used to intelligence to learn the various environment of networks. For now, we are not only talking about networks, and they act to dynamical situations. Many network aspects can be benefit from applying machine learning, such as network establish. We can acquire knowledge from the existing networks. So new network can be established with very minimal efforts. Only apply the different of the new network. Then the others can be automatically generated from the historic data. I believe one of the presentation today covered that aspect. Also, we can use machine learning mechanism for routing control and optimization. For that, there could be two directions. One is we remain the current routing system, routing protocol, and routing control plan. Then just apply the machine learning on the control plan or the way to computing the routing table. But on another side, more evolution way is we may be able to restructure the routing system. Routing system is already autonomic from the very beginning, but it requires many configurations to be able to start the routing protocol. But if machine learning can be applied in a very lower layer way, we may be able to bring up routing system without any configuration. That's the ideal way, maybe very long-term way. In the network management, machine learning could predict the future network situation. Then the network administrator could do something before it happens. For example, if they, from some running data, say the network administrator may find out devices may have potential to be failed in 1 or 2 days, then that one could be replaced or fixed, or they can learn in some certain time, maybe the day after tomorrow, in some particular place, the traffic could be reach the limit. Then maybe some dynamical solution could be deployed in that place. And the machine learning could introduce the autonomic and dynamical manager to the network. I believe that could be, one of the way we maybe, applied in the autonomic service agent, which we are already talking about that for a year in animal working group. The machine learning could analyze the network faults and support the recovery. I believe one of the topic today also cover that. For security, machine learning can learn the network attacks and their behaviors so that protection mechanism could be self-deployed, self-developed. The last button, also very important, we could unify the data structure and the communication interface between the network as an infrastructure and the upper layer customers, so that the upper layer application could easily obtain relevant data information. Next page. Okay, this is my last slide. This is the proposed network machine learning research group. We hope to provide a forum for researchers to explore the potential of machine learning technologies for networks. In particular, the NMLRG will work on potential approaches that apply machine learning technologies in network control, network management, and supplying network data for upper-layer applications. The initial focus of this group will be on higher-layer concepts and use case study. If we fairly form a formal research group, the research group is expected to identify and document requirements to survey possible approaches, to provide specifications for proposed solutions, and to prove concepts with prototype implementations that can be tested in the real-world environments. Okay. Oh, I use more time, which I assigned to myself. Any question? Okay.
Pierre Peloso. My question would be related to autonomic and machine learning. Mm-hmm. Would you consider that from your presentation, I had the impression that there's a need to have machine learning algorithm for having autonomous behavior?
Could be.
Or is it just one option among other algorithms?
I would say autonomic is one of the motivation we are doing the machine learning here. But machine learning could be, still could be, interacting with human operators. So autonomic could become, a very important aspect of machine learning applying in network.
I think his question was the other way. Like, can you have autonomic networking without machine learning? I think that was his question.
Yeah, more in this direction.
For now, I'm not sure. The first target for this group will be doing the higher layer concepts and the use case study. But given the time, that may be in scope. For now, I'm not sure. We are not still formally form a research group yet. This is a proposed research group.
No, yeah, I understand.
Yeah.
Okay,
thank you.
Kevin Falk, Carnegie Mellon University. The second bullet, higher layer concepts and use cases, seems like could be pretty broad. Could you discuss a little more in some detail what you would expect to be the initial areas that you mean by higher layer use cases?
For now, we are set very nearby for that. Anything regarding to the network and use machine learning mechanism could be discussed here. That says we are giving a forum for people to present whatever they think is relevant. But in the future, after a round of use case discussing, we maybe, narrow our scope to focus on certain use cases or certain solutions.
Okay, I was just wondering if you have some particular problems, things that you perceive as sort of pressing problems for which you think machine learning might be a great solution.
For now, I list the network control, network management, and supplying network data for upper layer application there. But that's not the limitation or burden there. It could be more. Okay.
Ulrich Levin. My question is, do you have a statement what you perceive as not being in scope of this effort? Have you thought what is not in scope?
So can I answer that? So it's a proposed research group, and the way it works is it's like pretty broad in scope. It's not like as tightly scoped as like a IETF working group. So I don't think it's going to be possible to explain it in a sentence, but I think we are in the exploratory phase of this. And by the time like Lars decides to either go with it or not, I think there should be a better idea of what is going to be in scope or not in here. But I don't think it's there yet at this point. It's very exploratory at this point.
So I will give you an example what I think about, like how it relates to the deep packet inspection, for example.
Could be. You need to bring out,
My question is, what kind of information you are going to collect on the network? Have you thought about it?
Yeah.
I mean, I'm sure you thought about it, but it's kind of relates to the previous question, I guess, or echoes the previous question. To be more specific, what kind of information we actually think of learning from the network in order to perform machine learning?
The case is, we are doing the use case study. So you guys need to, go front and introduce your use case or whatever you think in your mind. Then together we can learn, that use case and study them. After that, we can, become more clear whether that's in scope or whether the group want to take that further or not. So I do encourage you guys to apply the time slots for the next meeting or discuss your use cases, whatever, in the mailing list. Okay, until then, we are not clear.
Lars, do you want to talk to that or?
Yeah, Lars, I got maybe sort of, I think Zheng already said it, right? this is not an IETF effort, it's an IRTF effort. So it's a research group. There's not going to be standards coming out of this, at least not this group, right? It might influence something over in the IETF side at some point. But the point here is, it's to be a forum. If there's a lot of researchers that are looking at machine learning as a tool to apply to networking and other things. And, we want to talk about those sorts of research efforts and learn something from them, and maybe realize that, hey, this might actually fit into something we're struggling with over on the IETF side eventually, or not, right? That's another outcome. But it's mostly about judging for the next couple of meetings, and mostly about judging whether there's a community that's forming around wanting to discuss this together, here or not. That's really where it's going. That's why it is broad, as you said, and that's fine.
Thanks. The person at the left mic, then Eric, then Brian.
Right. So I think that's related
Your
to
name?
Gihan Dias from Sri Lanka. And so that's related to the previous questions about the scope. I believe network security would be a major scope of this. I think there's a lot of work already been done, intrusion detection systems and so on. Do you think that's very much in scope, or you want to keep out of that?
Previous. Somewhere I did.
Okay, so you're saying yes?
The
His answer is yes?
Yes.
Okay, great.
Eric?
Eric, not Mike. So you can actually go back to the slide where you have the list of things. Yeah, that one. So I think that, so based on my understanding of machine learning, there seems to be two different pieces here, broadly categorized. One is sort of learning by classifying, using machine learning to classify based on a large set of data that you get from the network, right? To see whether this is some network management event, security event, whatever, right? And I think that might be something that, is an interesting application of machine learning. But you have another piece here which basically says recovery or correct or routing or whatever, right? Basically, you're taking the results of that and then feeding it back into the system to change it. And I don't know to what extent that's been changed. I mean, it's one thing saying, Amazon gives me recommendations using machine learning. Okay, well, nothing breaks if they get it wrong, right? I might think it's crappy, but as opposed to saying, oh, it shut off that port because it thought something was wrong on that port. Well, now suddenly the network has fallen down and can't get up again because all your controlled plane traffic traveled over that port. Oops, right? That might be a interesting set of research that can be done there because you're looking at both what are local sort of learning things and corrections, whatever adjustments you can make on an individual device, as opposed to what's the network level, within some domain, right? What data do you gather? What decisions do you make at a network level event? So I think that it might make sense to split apart, as you think about this, the learning aspect and the action part of it, and feedback.
Actually, as I mentioned earlier, for many use cases, maybe machine learning need to be combined with traditional mechanism or combined with evaluation system, which is not machine learning. But case by case, we may not be able to only talking about the machine learning part. So for certain cases, we have to consider them as a whole use case. Part of them are machine learning. Yeah.
Hi, Brian Trammell. Actually, you answered half of my first question to Eric's question, so great. I'm happy with that answer. The second thing is, if you actually go to the next slide. So we're talking a little bit implicitly about the interaction between this proposed research group, should it be chartered, and the IETF, and sort of it's like, okay, well, there's products that come out of this research group that may be interesting from a standardization standpoint. I think there's a lot of value as well as with respect to flow from the information from the IETF into this research group. I think that one of the values of this as a forum could be allowing researchers in this space who maybe have less contact with sort of the day-to-day realities of networks and how they work. I've seen a lot of really interesting research in the ML space. It's like, okay, that's a neat toy, but that's not how the network works. So somehow finding a way to get people within the IETF who otherwise wouldn't come, be interested to come and sort of have interchange with the people in this forum, I think would be a very valuable thing to think of as the value of this working group, or the research group. Sorry, I see use cases and document requirements up there, and I think I'm in a WG meeting. That's a separate problem. Thanks.
Thank you. We'll certainly, help to have more interaction with the IETF, and in the future, if the group, research group decided something matter enough, we need to do the practical work, to do more standard work. We can, come together to form a proposal for IETF, I guess.
Yeah, my name is Jérôme François. One question regarding the scope of the proposed group and what you said before. I think in the core of the machine learning, there is also data, and will be also in the goal or in the scope of the group when you say use cases and I think proof concept with prototype implementation, that the group will also basically survey what data set we could use to maybe provide assessment of data set, to think regarding, yes, basically to have a common basis when we want to validate, for example, a use case?
To be honest, I'm by myself, I'm not sure about the fixed data set, because the fixed data set may be a very good way to evaluate the, the certain solution for a certain use case. Maybe that's easier to compare the different solutions for that very specific task. But, the network situation is very complicated and dynamic change. So if we can, do some work against the real world, environment, that will be, for me, better than the, fixed data set.
I don't mean explicitly fixed data set, but at least maybe definition what is a good validation regarding the data you use and things like that.
Yeah, good to do.
Thank you.
We go to the back mic.
Stephen Wright, AT&T. Just looking at the last bullet there and the words document requirements, which seems a little odd for a research group. If the purpose is to deal with requirements, then those requirements should be on something something specific and related to some overall objective, which is probably beyond the scope of a specific research group at the moment. So I'd suggest to either really expand what you mean by what type of requirements you're trying to collect, or just delete those couple of words.
Okay, could be. I mean, so far we haven't, I mean, that could be some study result from the use case. Then we'll see in the future.
A couple of questions.
Can you please state your name?
Oh, I'm sorry, Andy Veach, Netcracker. Some questions were asked about data sets. My broader, or use DPI or, syslogs or whatever. My general question is, you need a lot of data and a lot of different scenarios to do all this. I don't know, are there open source, open access to all this data from lots of carriers? You also need real world data, not simulated data. Has anybody addressed an issue of making data sets from network management from real carriers available for researchers?
For me, for now, there's no answer. That will depend on this group. If people are volunteer to provide some data, and other people are interested to use that data against certain solutions in certain use case, I'm fine with it. We cut the line after you. Whatever. Yeah, go ahead.
Go ahead.
You're good to go. Yeah.
Okay, thank you. So trying to be practical and to understand better what can be done here or what you are planning to do. You say it's a set of use cases. So how would you describe a typical use case? What it will be consist of? You know, what would be a template for a good use case?
Templates. Okay. I never think in that way. I would say I try to not give any limitation or what for you. You can come in front and describe what you think to apply machine learning in a certain aspect of network, whatever the network aspect is. Then you may describe how you solve that use case by using machine learning mechanism, and you maybe measure your result against the real world usability, or you may say that something could improve. Okay. Nas, you do have the priority.
Yeah, Lars, I think we're falling into the trap and behaving like we're in the IETF, right? You need to understand that in the IRTF, the charter almost doesn't matter. The charter is more an advertisement to researchers so they understand what kind of stuff happens in the room when they show up. And so the particular words here to me are, the first paragraph is interesting. And then then whether somebody comes with a use case and says, maybe, we've applied machine learning to spam and here's what we found, or that could be described as a requirement, right? Or a use case. But think of this as an advertisement to researchers to come here and present work. So it wants to be inclusive. And so that's really all that there is to it. And the first meeting is not the meeting to talk about this really, because that we do in a year, or after you guys have met a couple of times and actually really understand what you want to do and what has worked. And then we can talk about the details of the charter. For the moment, it's just an ad.
Thanks, Nes.
Thanks, Lars.
Okay. Next. Jeremy?
Good morning, everybody. So, yeah, I'm pleased to present this work, which is entitled Multidimensional Aggregation for DNS Monitoring. So, as we have seen before, there are many different use cases for machine learning, and one part, I think, which is very close and related to machine learning that has been introduced is also, first, you have to select some features and to represent some features. And this is mainly my goal today is to show you doesn't work. Yeah, so idea is in this work to show, before applying any kind of machine learning, to think about what will be a good way to represent the data you want to work on. And I will mainly motivate this with DNS monitoring, but it's only one use case. Sorry? I don't have PowerPoint. Does not work. This first page is working.
So Sheng, my suggestion would be you move to the next presentation and figure this out while the next speaker talks, since we're running late.
Could you?
I'm going to try.
Try.
Okay, hello. So my name is Albert Cabellos. I'm a professor at UPC, which is a technical university in Barcelona. I did this work as a visiting scholar in Berkeley with Professor Jan Valbrand. And this is really ongoing research. I started around 6 months ago, so there are many things which are still ongoing. So this is not really working, so if you can go, okay, thank you. So this is acknowledgements. Next slide, please. Next. So the main goal of my research is to try to find use cases of machine learning applied to SDN networks. And I'm focusing pretty much on two different areas, which is control and management. I think that there are many ways to define control and management. Let's say that at the end, I'm thinking about control as fast dynamic, things that happen very quickly in the network, like routing or resource allocation or optimization in general, congestion. And then management is something that happens quite more slowly and that typically has like human times, right? Like network planning or resource management as a slow dynamic or load estimation. And then any use case related to recommendation mechanism. I think that in the long term, we will be able to build, as he was pointing out, Sheng was pointing out, self-driving networks, right? I think that this is in the long term. I'm leaving out of the scope of my research all the use cases which are related to anomaly detection and traffic classification. I think that they are fantastic and they are very well understood, and there are many commercial applications of these use cases. So this is completely out of my scope. So next slide. So why I think that this is relevant now? There is a paper from David Clark, 2003, SIGCOMM, which is entitled A Knowledge Plane for the Internet. And on that paper, David Clark, he pointed out that instead of having traditional algorithms, we should move to something that he calls knowledge plane. So something that understands and learns how the network works and then applies some configuration or optimization. So I think that what I'm going to say is not new. David Clark said it in 2003, and it's pretty much the same view, trying to apply this kind of artificial intelligence techniques to networking. Why I think that now they are relevant? Because the network traditionally has been a distributed system, meaning that each node of the network has just a partial view of the entire system. Plus, it only has typically partial actuation capabilities. What SDN brings into the picture is centralization. So now we have a central entity that can have a full view of the network and can have a full control of the network. And I think that that's a big paradigm shift, and it's way easier to apply this kind of techniques when you have a central entity than when you have a distributed entity, a distributed system. On the other hand, I think that another important driver of this new area is that typically networks have been monitored with NetFlow, SFlow, SNMP, and so on. And this has worked great. But right now, routers and switches, they have CPUs, storage, and so on. And they can provide monitoring tools which goes well beyond these very well-known protocols, so that we can have very good telemetry of the network. At the same time, we have a central entity with full view and full actuation capabilities, and this is a good fit for machine learning. So that's pretty much what I think that are the drivers of this research. So next slide, please. The architecture at this point is very, very straightforward. We have the network, and then we will have some sort of telemetry infrastructure, which is receiving data from the network. We have some sort of intelligence, and we have some sort of broker which will act upon the network in some ways. I think that the main idea should be to learn something about the network, then build a model of the network, which is something that we don't have. Yeah, we have some models, but not as the ones that I'm discussing right now. And then provide something to the network, which is typically can be optimization or autonomic management, or in general recommendation. Like, you should upgrade this link because this is happening, or you will get a way better performance if you upgrade that interface. So next slide, please. So here I'm going to go through a list of use cases, and at the end of my presentation, I have some very preliminary results. So the first use case is on overlay routing. So overlays are right now quite popular, and in overlays use cases, in many cases, the underlay is unknown, right? The underlay that I'm using is not known by me. There are many reasons for this. The first reason is that it's because it's provided by another company, so I don't have any control over the underlay, or because it's legacy, so we don't have any kind of telemetry or SDN capabilities, or because it's a use case such as VPN providers over the top. There are many use cases where you don't see the underlay. And let's say that the underlay typically may offer a set of paths to reach certain destinations. This can be at the underlay or overlay layer. You can use segment routing, or you can use list for that. So there is a very well-known problem in this kind of networks, which is, okay, I have a set of traffic from the overlay, and I have to assign traffic to path such that I achieve certain objectives, which can be not to bottleneck the underlay, not to bottleneck a leak of the underlay, or to achieve certain delay guarantees. So at the end, I think that in general, this kind of use cases are learning how to route with information that is hidden, which is in this case is the underlay. So next slide, please. So here I have, let's say, a picture of what I was saying. So you have an SDR controller, which is controlling overlay nodes, which are blue. And each overlay node has to transmit traffic to another overlay node. It has a set of paths which go through an underlay, which is hidden, right? So I have to choose which path, how to allocate traffic to the path so that I achieve the SDN controller that is controlling all the entities achieve certain objectives, as I was saying, load balance or delay. So next slide, please. So here I have identified, let's say, two sub-use cases, which I think they are relevant for this case. The first one is that can we learn the performance of the path, and can we try to predict which is the performance of the path at the overlay level? So again, I don't see anything about the underlay. Can I predict something about the overlay path? If you take a look to the literature, you will see that this is quite well known. And typically we have used time series since paths typically exhibit a seasonal behavior, also for the performance. And I think that this can be improved by learning correlation with external events, such as, okay, so the overlay node can learn, okay, I have seen that this is seasonal, but tomorrow it's a holiday here in geographical region. And I have learned that whenever it's a holiday, traffic changes this way. And I have a best delay through this path. Or I can correlate with weather. Okay, tomorrow it's raining, plus there is an important sport event. So I know that when this happens, these links get congested. So I should use another link. Then can we predict failures and blackouts? Well, that's a tough question. I don't know, honestly. If the failure is completely random, then of course we cannot predict it. If there is certain information, such as the failure is for whatever reason, or the blackout is correlated with some performance events before this is happening, or it's correlated with some BGP signaling, then yes, we could predict this kind of failures, but I'm unsure of that. Okay, the second, let's say, sub-use case is trying to find correlations with the traffic. So let's say that here, again, we are this SDN controller, we are controlling these blue nodes, and I have choose the path to follow from A to D, I have chosen the path 2.6. And from B to C, I have chosen the path 4.5, right? So again, I don't see anything about the underlay. The underlay is hidden for me. Well, whenever I choose this configuration, what I can learn is, well, I learned that whatever I choose to allocate traffic through this path, for whatever reason, I see a spike on the delay. So maybe this means that those two paths are correlated and they are not disjoint. So maybe I have to choose another configuration. So again, the things that we could learn from the overlay. So next slide, please. Okay, this is a new different use case in a different scenario, which is NFV or SFC, and in general, it's resource management. This is a very well-known area in data centers or cloud computing. Here, what we have is we have a virtual network. Let's say that we have switches, DPI, firewalls, and routers in general. And what I need is I need to run this virtual network in this data center, right? So what I need is to allocate each function, each network function to a virtual machine or a virtual network function, and to run it on a hardware, right? And then I have to change these virtual servers. This is a very well-known resource management problem in data centers or cloud computing, and it is typically solved with optimization techniques, right? Here, what we could do is, and I have an experiment that I will show later about this, is, okay, but can we predict what will be the performance of the virtual network function? Can we predict what will be the performance of the router, of the DPI or the firewall? And can we predict what will be the cost in terms of CPU of this virtual network function? If we can do that, that could be very useful to resource manage this infrastructure, because I know how to allocate things and I can predict which will be the performance. Then if I have to fulfill an SLA, then I will be able to know if with this configuration, I will be able to fulfill such SLA or not. So next slide, please. Okay, this is another use case, which is in load estimation. I think that predicting which is the load of the infrastructure, now load is whatever you want, is whatever load means in your infrastructure. Predicting this kind of metric, I think it's very relevant. And I think that you can do this in two different time scales. If you do this in the long term, meaning that you are predicting things in months or even years, this can be useful to understand when you will need an infrastructure upgrade. And this should lead to reducing the infrastructure replacement cost. If you can do this in the short term, which means in the next hour, well, you can anticipate congestion or performance degradation in a link or in a service, and you can move from something that it has been, I will think, very inherent to networking, which is just-in-case provisioning to just-in-time provisioning, right? We have been over-provisioning things. Well, with this kind of learning, we could move to something which is just-in-time provisioning. So next slide, please. Next one. Yeah, so here, the kind of metrics that the kind of plots that I think that could be really feasible to perform, to produce is, okay, I have the relation, the machine learning learns the function which relates the number of clients that my network has or subscribers with the load of the network, right? So this is today, and then I expect in the next year to have this amount of clients. So this means that I will be in this load. Then next year, I expect to have this amount of clients, which means that I will go through my current capacity. So I need to plan ahead and do something. Or we could do this with the amount of services as well. So next slide, please. So here, just for the record, I have suggested the kind of techniques and metrics that we could use to achieve this kind of plots. So next slide, please. Okay, this is another use case, which I think it's the one, at least in my very personal view, that will have a better, it is easier to deploy and more simple, let's say. In this case, we want to extract knowledge from the network. So the network is providing lots of data, huge log files, which they are very hard to understand in raw. And what we can do is use machine learning to extract knowledge out of this, all this data. And then this knowledge can be sent to a network administrator, to a human, such that the human will act upon the network. So as Sheng was pointed out, I think that it makes a lot of sense to start thinking for the short term of this kind of use cases where we don't have a closed loop, we have a human in the loop, which makes things easier. And also, as someone else was pointing out, if for whatever reason machine learning is providing bad knowledge, then we always have a human which will understand that this is not relevant, so it won't do anything. So next slide, please. The kind of, this was also pointed out by Dave Mayer, so this is a use case that he suggested. So it's pretty much the same, right? The kind of knowledge that we could extract is, okay, I have seen out of the log files, machine learning could learn, okay, I have seen a high number of BGP updates messages, which means above the average. And at the same time, I have seen that this interface is flapping. So, well, if you send this to a network administrator, I'm sure that he will know what to do. Or I have seen that jitter in this interface is above normal, service XYZ latency is also above average, and clients for service Y is higher than the average. So again, network administrator, it's pretty obvious that we have too many clients in this service, which results in many other issues. So next slide, please. Again, here I have showed a little bit which kind of techniques we could use to achieve this kind of use case. I think that principal component analysis, correlation analysis techniques in general, or k-means should be useful for this use case. So next slide, please. Next one. Yeah, and now I'm going to show some experimental results, actually two different set of experiments. The first one is, let's say, finish it, and then the other one is really ongoing. So next one. Yeah, next one, please. Okay, here this one is related to the use case on the virtual network function. So here what we want to prove is, can we learn which is the cost of a virtual network function? So can we, so we have a virtual network function, which is a firewall or a DPI or a switch. And then what we do is we send traffic through the virtual network function, and we want to learn this function. In this case, is the cost. Okay, so if we know if we can see the traffic that the network function is going to process, can we estimate which will be the CPU? Okay, so the predictor in this case is the traffic, and the predicted in this case is the CPU, but the model should work exactly the same for the delay or for the latency which this function introduces. And this is a key thing because here we are assuming that the VNF is a black box. So we don't know which is the type, we don't know which is the configuration, we don't know anything. We just know that there is a piece of software that we are running, and we only see traffic going through and CPU consumption. So next slide, please. So in this case, the virtual network functions that we tested were real ones. In this case was a switch, a firewall, and a DPI. All of them configured in a reasonable, realistic way, let's say. And for traffic, we use real-world traffic from my university. And in this case, we trained a neural network with 3 layers. It was a pretty small neural network, so this is a pretty straightforward experiment. Next slide, please. And then how we represent traffic. And I think that this is one of the, I think that in the previous discussion, I think that so the hardest part of this experiment is how to engineer the features, right? So how we represent traffic in a neural network. And I think that could be useful to provide examples of features. And in this case, what we did is we defined 70 traffic features. So we get 20 seconds of traffic, of real traffic, and we define 70 traffic features. All the traffic features are very simple, and they can be computed at line speed. It's a list of 70, right? So let's say it's number of packets in the 20 seconds batch, total number of bytes, average inter-arrival time, standard deviation of the inter-arrival time, how many different sources I have seen, how many IP destinations I have seen, how many IPv4 packets, how many IPv6 packets, and so on. So there are 70 traffic features which can be computed at line speed. So next slide, please. So before getting into the accuracy of the model, what we ask ourselves is, okay, we can learn this model and we can predict which is the cost of a virtual network function just taking a look at the traffic. But is machine learning an overkill? Do we have any other kind of techniques like linear regression which are easier to implement? Well, so what we did is we took a look at the model that the neural network produced, and we found out that there were actually nonlinear relationships, and actually quite complex relationship between the features and the estimates of the CPU, which means that it makes sense to apply machine learning, and other kind of techniques should perform way worse. Then we also, next slide, please. So this is the accuracy of the model for the 3 virtual network functions, which the error is in 95% of the cases below 5%. This experiment is just to show that, to prove that we can do that, and that it makes sense to learn. And I would like to point out 2 things. Is that what we found out is that first, the model was not trivial, so machine learning makes sense. Second, that the virtual network function is a black box, so we don't know anything about the virtual network function, but still we can learn. And that different virtual network functions, they depend on different traffic features. So the neural network, what does is, it sees the 70 traffic features, and it will pick the ones that are relevant for that particular virtual network function. It will learn which are the good ones. And different virtual network functions depend on different traffic features. So that's why you need a very wide set of features and let the neural network decide which are the good ones for this particular network function. And also something that I think it makes sense for many scenarios is that you can take, if you know something about the virtual network function, you can take the virtual network function, you can put it on a lab, learn how it behaves, and then take the function and use it in your data center. So you don't have to learn in your data center. You can do this offline and just pick the function that you have learned, if you assume that you know something about the network function. So next slide, please. So this is the last set of the last experiment, and in this case, yeah, next slide. Yeah, here. So here what we're trying to do is, can we learn how to route? And this is related to the overlay use case. This is a more academic experiment, so don't think of it in terms of how I could apply exactly this to a real use case. It's more, can we learn how to route? This is the question that we ask ourselves. And what we did, and at this point it's something very simple. We took the Internet 2 topology in the US, and we assume 5 different routing policies. So again, this is very simple for IETF standards, right? So it's a very academic experiment. And which are one, which is I will take, so here is each node has to decide which path, so it has a traffic, there is a traffic demand, and I have to choose over which path I will send the traffic. Then I can choose among 5 policies, which is 1, I will send all the traffic through the shortest path, or 2, I will distribute all traffic among all possible paths, which are limited to 10, or 3, 2/3 of the traffic through the shortest path and 1/3 through the second shortest path, and so on. Next slide, please. So here we try to learn this. So if I create a model, I don't know anything about the topology. So the topology is completely hidden to me. It's an overlay use case. So I have a traffic matrix, and I have a routing policy, and I see the delay of the, so if I have this traffic demand over this topology which is hidden, and I choose this routing policy, I end up having this delay. Okay, can we learn this without seeing the topology? So in the future, if I see a traffic demand and I choose the routing policy, this routing configuration, I know that I predict that I will obtain this delay. So can we learn that? So next slide, please. So this is an ongoing result, as I was saying, and using a little bit, quite large, well, not large in terms of Google, but large for us, neural network with 1 hidden layer and around 200 input features. What we obtain is that, yes, this is the estimated value. No, this is the real value, and this is the estimated value. So this straight line means that we have a perfect accuracy. And in this case, we have around 5% of error. And the answer is yes, but in this case, we only had time to run the experiments for 1 traffic policy. So we were assuming that all the nodes were using the same traffic policy. So next slide, please. So as a summary, I think that at least that's my personal opinion, the use cases where machine learning makes sense in networking are the ones that traditional models are not practical, because we have plenty of models for networking, right? And they are very good models. But in some cases, those models, they are not practical. And there are mainly 3 reasons for that. Either because they are computationally too expensive, because the problem is NP-hard and you cannot explore the entire solution space of your model, so you need something else. Typically, you rely on heuristics, while here you can rely on machine learning. Another use case is because in some cases, although we have the models, there are many hidden variables that we cannot see. And for this, machine learning makes a lot of sense, such as the underlay case. Or because they are not accurate. When you start thinking about modeling a network with different traffic classes and different schedulers and so on, well, then models, they are not so accurate. So again, machine learning could make sense. So that's pretty much it. So thank you.
Questions, discussing?
Hi, Ed Henry with Brocade. I have a question regarding the model that you used for routing. How did you handle the coordination within the system? I know it was strictly academic, but what are your thoughts around handling coordination between 15 different boxes that all have a different model, but they...
I don't have an answer for that.
Okay.
What we did is we assume that there is a certain controller which has all the information.
Okay, so you're assuming it's a controller-oriented.
Yeah, we assume that there is a controller and that has all the information.
Thank you.
Hi, Pedro Arana, Telefonica. Very nice presentation. Thank you. Very interesting insight. Just one very specific question. Maybe it's my NFV bias. You say you've been using this on the data center. All the things you were showing seem to make sense. However, I still see lots of well, how can I say it? Have you studied also things like virtual network function placing, which is going to be very aggressive sometimes on the results you get?
Yeah, so we didn't study virtual network function placement. There is a bunch of papers which they are into virtual machine placement, and we should start thinking about trying to apply them, and let's see if they work. I don't know if we can apply them directly. What we did here is, let's say that you have an algorithm to place your virtual network function, but which is the cost of each virtual network function? How do you know what will be the cost? You need to learn something about it. And if you have a chain of functions, which will be the delay of all the functions all together? So you need to learn. And this is what this kind of models will provide you. Then using these estimates, you can place them in a more efficient way.
Thank you.
Thank you.
Hi, Giovanni Mode. It's at EN Labs. I just wanted to point there is the moderator showed the black box for prediction. You can send a paper around. There's a paper from Chomsky, and he criticized the sort of model. I mean, he said that it's used, but you got to be careful with that because fundamentally, you're not learning much of that because you just treat it just as a black box. So it's like if you would observe the world and try to predict, like, for example, Newtonian laws, just observing throws a lot of data in that, but fundamentally you don't understand how it kind of works. So just to criticize, I think it's a different application, but you just got to be aware of that. It's useful, there's use, but you're not really understanding how fundamentally the network works.
I fully agree with your view. Fully agree. I think that if we have a model like a queuing model, I don't think that machine learning makes sense. Now, there are many scenarios where we have a model, but when we want to solve our problem for a very large network, we cannot use the model because it's computationally too expensive.
Yeah.
Right? And then people typically solve these kind of issues with heuristics. Now, heuristics and machine learning, well, they have the same understanding of the network, which is none, right? Mm-hmm. It's more a black box. But I agree. If we have a good model and we can run it and we can use it to solve the problem, then I don't think that we should use machine learning. The second scenario for machine learning is, in some scenarios, we don't have all the information. Let's say that, as I was pointing out, the underlay is hidden, or we don't know the topology, or we don't know what virtual network function we are running because it's a black box, because we are in a multi-tenant data center. Then we cannot have a model. So again, seeing the things as a black box makes sense.
No, yeah, I agree with you. It's just like we got to be aware of that.
But I fully agree with you. We should be aware of it. So it's not a solution for everything. Not at all. Not at all.
And I use it, so don't get me wrong.
Okay, last one, cut off after you.
Okay. Fei Song from Beijing Jiao Tong University. And very nice talk. And could you please just go back to the from data to the knowledge? Yeah. I cannot remember which slide.
I think it's just
right here. So could you please just share any understanding related with the knowledge? What do you think?
Yeah. So
how to define the knowledge?
Yeah. So network monitoring provides data, right? Which are at the end log files, huge log files with many information, and a human cannot parse this kind of so much raw information. Now the thing is, let's say that you give all this log file to a machine learning, and you tell to the machine learning system, look, so you need an expert to train it, right? So what you will do is you will take the log file, and an expert will point out events that are relevant. Okay, an interface flapping, an interface going down is a relevant event. Too many BGP messages in a certain period of time is another relevant event. Now, machine learning, what we'll do is, and for this you can use k-means or correlation analysis, it will try to find correlations between events which for a human are relevant, that are correlated with other events of the network, and will create knowledge, which is like something that will give to the human and will tell, look, this event that was relevant for you is happening right now. And at the same time, those other events are also happening. Then a human should do something about that.
Okay, so here comes my, here comes my comments, maybe not for this talk, for the research group, is what is the boundary of this research group? So things based on that slide, we want to use machine learning for the network management or the other perspectives. So do we think that the prediction is enough for that use cases? So if we say the prediction is enough, I think it is perfect work. It's like we can, predict the usage of CPUs or other things. But if we want to use this achievement of research group in other perspectives, so maybe we have to consider other things like the gaming theory. For example, I have two paths. One is really fast in terms of the bandwidth, but it's really slow in terms of the delay. Another one is just another case. How should we just choose which one is better? Okay, so I don't know. It's just a comment for the research group. Thank you.
Let's take that to the main list. We're running short of time.
Thank you.
Thank you. Okay. Yes.
Bring a laptop.
Bring your laptop.
Bring a laptop.
My laptop?
Yeah.
So yes, again, me coming back with the presentation on DNS monitoring. So yeah, you can go on next slide to the motivation. Yes, again. So what I was saying just before is, so I will rely on the DNS monitoring use case to show you that first, the first thing you have to think about when doing some machine learning and basically some any kind of let's say techniques about that you want to use, for example, here to detect some malicious activities is to think about features and how you represent features. So yes, we all know that with DNS traffic, if you're looking into your DNS traffic, you can find something very interesting, for example, related to botnets, to phishing activities. So it's a very well-known type of data that you can rely on. And something which is interesting is that you can also collect it easily is, for example, with passive DNS monitoring. It's not so much to collect compared, for example, to full packet capture or flow-based data. Yes, really smaller data to collect. So our goal is that we have collected DNS data over multiple weeks, and we try to see if there is some basically malicious activities within it. So yeah, you can go to the next slide, please. Next. Okay. So yeah, and it comes now to the aggregation because, okay, how you can monitor, let's say, malicious activities in DNS record is that, for example, you will easily, you will try to see for a domain name if, let's say, the variation of the volatility of IP addresses is very high, it might means that there is a risk. Of course, IP addresses can change because, for example, a float balancer and things like that. And so usually what you do is that you define a kind of threshold such that you define the size of the network that you think that it's okay, so that the domain name can change over time. So it means that firstly you have to fix manually this kind of threshold. And on the contrary around, for example, you can say that an IP address which is always assigned to the same domain seems reasonably good, and when it's always, let's say, assigned to another domain, again, it might be a bit risky. And so you did this kind of monitoring by hand, and you define finally you are not looking at IP addresses, but more some networks. And then so you have to do some monitoring over let's say, aggregated data over networks. And again, you don't really know what should be the reasonable size, basically, of the prefix you want to monitor. So you can try different ones. And this come to us not originally for DNS, but just for flow monitoring. So this was basically the IETF aggregation that then I will apply to DNS comes first with just flow monitoring. So here you can see what has been proposed by others, in particular by Haguri, is just to represent the data you collect over trees that represent the hierarchical and natural, let's say, aggregations that you can do over some networks. Where at the end, so you have the different subnetwork and the hierarchical representation. You have here the subnet which is represented and the volume of activity. What is the volume? It can be whatever you want. It can be, for example, the number of packets that represent regarding the entire monitoring you do. It can be the number of bytes, or it can be the number of alerts from an IDS and so on. Okay, next slide, please. So, the advantage of this representation is that you don't need to fix a priori, for example, what is the size of subnet you want to monitor, because you monitor everything until a certain level, which is not defined by the prefix length as usual, but more by the minimal volume of activity you want to monitor in this subnet. So we apply this to multi-dimensional case. So we have something very easy. We have two kinds of aggregation. First is temporary, just split by per time window. And then here's spatial, which means that exactly what I said, you just keep nodes that have at least a certain level of activities, but not on single dimension like IP addresses, but maybe on 2-dimension IP addresses or IP subnet and domain name. The thing that we propose here is usually when you want to do that, for example, with maybe subnet, you will different IP addresses, source and destination. You will first, let's say, aggregate over sources and then aggregate per destination, or the other way around. But you have to fix it manually, which is it means that it's really human-tailored monitoring. So first thing we want here to promote is that we propose an approach as you don't have to specify what will be the order of the data you want to monitor. For the first dimension, you don't need to, for example, if you want to first aggregate over domain name or IP addresses. It can be in both directions, and we see it can change over the different layer of the tree. And of course, we don't want at all to specify any, let's say, granularities. This should be guided by the volume of activity. Okay, next slide. Okay, this is just flow, so you kind of data sets that you use at DNS. So you can go to next slide again, please. So here is an example. So it's the same tree than before. So now we have added two other dimensions. One is the type of application, and the other one here we have source and destination IP addresses. So as you can see sometimes here, so you can go in 3 directions. What you do in 3 dimensions is 3 directions. It means that here we'll be more specific regarding this node into these 3 dimensions. Sometimes you have only been specific on certain dimension. For example, here you can see that the same for the application we are not more specific. And going like that, sometimes you can go again further and further. So maybe here you will be more specific in this dimension, maybe here in only destination subnet, maybe here in just only for the type of application and so on. So basically, there is no order between dimensions. It can change along the path you are aggregating data. Okay, next slide, please. Next slide again. Okay, so MAM. MAM stands for multidimensional aggregation monitoring. So it works like that. So of course you have the kind of data parsing, then you create the node, you insert the node into the tree, and which is very important is aggregation. Aggregation can occur in two on trigger and two events. First, at the end of time window, basically you want to only keep nodes with at least a certain percentage of the activity. It's the main case, but also between the construction of the tree, because we want also to keep efficient our approach, and we limit the size of a tree, meaning that when the tree is too big, we just try to already aggregate it during the creation in streaming mode. So what is important to see is that the user, of course, has to specify the data he wants to analyze and to specify also how to parse this data and what is the model. And model, in that case, means the user only to say what is, to describe the hierarchical relationships within each dimension. Next slide, please. So yeah, underlying data model can be usually with IP addresses, it's just next bit, which just help to distinguish between different directions. You can define any taxonomy like that, which will define the different dimension. And of course, about domain name is as well very easy because it's hierarchical as well. Next slide, please. Okay, so the core of MAM is the tree data structure. So it's very close. In fact, if you look at the aggregation process, and if you know a bit is about density-based clustering, it means that you will create basically nodes where you have more nodes where the data are condensed over all dimensions. The main difference is that it's built in a kind of online mode or streaming mode, that you will not wait for all data to build your cluster. You will create basically on the fly. And this, I mean, by analogy, this cluster represents basically the leaves that you have in the tree. So as I say, we have to define direction, and then you have to insert a node. So if you go to next slide, please. So yeah, imagine you want to insert this kind of node. So there are different cases. There are very simple cases. So there are the cases that you have already this node into the tree. So using the notion of direction, which is based basically on the hierarchical relationship, for example, the next bit for IP addresses, you can easily go down in the tree until the leaf or node which differs from this. So if you find a similar node, you just update the activity volume here. If you find a node, sorry, a node which differs, first you will check if maybe this one is a child of the nodes you have found by just traverse the tree. And of course, if it's completely different, which is the most, let's say, complex case, which here, you have to create a branching point. Next slide, please. So yeah, branching point means just compare with the previous tree here. This node now is inserted. I think it's this one, yes. It's inserted with this one, and so we create a new branching point between the previous nodes and here. Okay. This is really how it works, and you create, okay, from an empty tree, and then you insert node like that. So either by creating branching point, updating an existing node, or sometimes and just creating a new child. Thank you. So the next slide is, so yes, aggregation, as I said, can occur at the end of a time window or when the tree is created because it's too big. So we have different strategies in that case. The first strategy is that, okay, no, the tree is too big. I will completely try to collapse it, basically. I will perform aggregation from the root and only keep nodes with a certain level of activity. And for the user, of course, when you aggregate, you just you just aggregate the activity into the upper node, okay? And the other case, which is more meaningful, but which is a bit more complex from a computational point of view, is that you use less recent use algorithm, so that you will first remove or discard nodes or aggregate nodes which have not been added or modified recently. This is to avoid that, for example, when you perform aggregation and that a node has very few activities, might be the case because the activity regarding this node, so this subnet, this domain has just started now. But it doesn't mean that in a closed feature it will not change. That's what we prefer to use the LRU. So now is the case for DNS. Yeah, next slide, I think just, okay. So yeah, so MAM is just perform aggregation, and just at the final, what you will have as the output is just a sequence of trees, but it does not tell nothing about what happens. For example, in the case of DNS, what happens if you can see domain malicious domain names. So, of course, we like trees because something that we have been used to use and to handle. So you can define a lot of stuff about trees, metrics, distance, and so on. We can do also some visual inspections. I will be back on that at the end of the talk. And of course, you can, if you define metrics and so on, you can perform automatic analysis. Next slide, please. So what the user has to say is, again, give the data, say how to parse the data, what is the model that is used for the data, means the dimensions, and some parameters. Aggregation threshold is the minimum volume of activity you want to have. So in case of DNS monitoring, will be the number of hits for a domain name, from a couple of domain name IP address you want to have. Oh, sorry, for a domain name and some network, because we do aggregation. The time window, the maximal number of nodes, and the type of strategy. Here you have the default values that we have used. And so next slide, please. So we put together domain name and IP addresses in the same data structure. And the idea, as I said before, is not to look, for example, when a domain name may have a lot of different IP addresses, which are mainly, let's say, scattered over all the IP space, or is the other way around, when IP addresses is mainly used for only a different domain name, which is also a very strange behavior. So we do some experiments on that. Next slide. Okay, we have this kind of data set, which has the name, and then we have the IP address. And so the volume activity metric would be the number of hits we have in this kind of database. Next slide. Okay, here I think it's quite easy to just perform aggregation over a domain name IP addresses. So at the end we have subnet, or here we have underhost, and okay, this is a very simple example. Can you go next slide? I think you can skip. Okay, this is a data set, but you can keep it. Oh, well, we'll go to the experiment afterwards. So yeah, we have a time series of trees. And what you want to know if let's say the volatility of IP addresses or domain names is stable or not. So we define metrics over all of that. Next slide, please. Yeah, you can juke. Yes, again. Yeah. Here it is. So just to give you some overview of the metric. So the first thing we have to do is we basically want to when we have a tree at, for example, time t1, we want to know if a node in this tree, for example, the node in one, has been seen, or a similar one has been seen in the previous time window, so in the tree t0. So we want to compare node per node first. To compare that, we just, for example, compare. Of course, we will have, we define a similarity metric, which should be basically 0 if, of course, subnets or domain name are completely different or disjoint. In that case, we define that as 0. But if we have one which is child of the other one, then we can define, just simply look at the number of bits which are in common for IP addresses, the number of common terms in the domain names that, I mean, the common, common name in the domain name which are the same. And we just also look at the difference in activity volume. So we combine all of this into a weighted metric here, where we look at the similitude both in terms of IP addresses, domain name, and activity volume. Next slide, please. Yeah, yeah, okay. So for the similarity metric, so now we have a similarity between two nodes. Now it's time, for example, to evaluate if a tree, for example, the tree at T1, here's the activity that it represents is very similar to the previous one. So for each node of this tree, we look for the most similar in the previous one, because we think that it's really what we look if we have seen the same activity before. It's here the first line, so we are looking for the most similar node. Of course, we have some also some how to say, we have some waiting over time as well. And then we compute the persistence of the tree by looking at all nodes of the tree at T1, by looking at the steadiness of each node, which is, yeah. So we will look for each node, the most similar in the previous tree, to compute the metric I described before. So next slide, okay, I will go very fastly on results. So here it's what we apply with the metric. So here you have, so it's not 100% of malicious data, we have a data set where we have malicious domain names. So we collect real data from our network, and then we apply blacklist to see where are the bad domains. And then we vary, basically we just remove or keep the malicious data we have from, so we keep everything, or we just keep only 0.1%. In all cases, of course, more you have malicious data, it's more visible, but in all cases, you can see that this stability metric over the aggregated data is relevant, because you can see that there is always a decrease. And if you go to next slide, so here what we do, we just sanitize the data set every 5 weeks. We remove all attacks. And so we see when we apply, when we again just keep the attack and we apply the metric, we just see there is a decrease. Okay. So this one's a macro analysis. It means the persistence of the tree. You can see that there is something which changed over time in this tree. It's very different than previous time. And then once you have identified once there is something bad, you can try to look what is bad. And to see that, you are more looking now at what are the nodes which are the less stable over time. And it's what we did here. So then you can use, for example, a threshold. And you can see that basically here, if you look at the true positive rate, you can easily exclude around 70% of the malicious domain name very easily without having too much false positive. Okay. Next slide. So yeah. Okay. So with what I presented, we can use aggregation is very interesting because and performant, because it has two properties driving this. First, it reduces the scale of the data you have to analyze. And in machine learning, it's very important because sometimes algorithms can be also quite computational heavy. So this is also very important. It really reduces the scale of data. And on the other point, it's also just not compress information, but also reveals some behaviors. Because, as I said before, some behaviors you can only see them as aggregated. For example, you cannot look at the individual match between an IP address and domain name, because there are cases, and of course there are existing cases where the IP address is changing over time, which is normal. But which is not normal is that, for example, when IP addresses is changing from one part of the existing space to a part which is completely different in time. Okay. But just to give you an overview of the difference. So we have an average of 2,200 nodes compared to here IP addresses and domain names that you have. Okay, I think that's yeah. You can skip this. I think this is where okay. Yeah. Oh, you can skip for this. I think we. Yeah, that's fine. I think I can now take any questions.
Okay. We take a maximum 2 questions. Sorry for the short term.
So it seems like the technique is very dependent on domain name stability compared to IP address allocation. How do you deal with content distribution network domain names, which exhibit a lot of the same kind of behaviors that your technique seems mostly to be focused on? And then additionally, how do you deal with malicious use of domain name parking, where they register a domain name, leave it there for extended periods of time, which would increase its stability, and then only activate it when needed?
Yeah. So thank you for the question. So yeah, for CDN, yeah, you're right. So we have also the same kind of behavior. Difference usually is also depends on where you collect your data. Because here, I didn't present it, but the case is that if you collect the DNS record really at a single network, for example, at only university network. And in that case, most of the case, CDN is the IP addresses are still, let's say, restricted to a certain subnetwork. And in that case, that's why also the aggregation helps. But the idea of this technique is that you don't have to specify, for example, the size of the subnetwork, so pressing lengths. And the goal is that you also look over time. And for example, if you have seen this domain Normally, so as machine learning, so you try to first have a data set where you have non-malicious domain. So if you have seized this domain, that you have been able basically to scale what is the dispersion of IP addresses, thanks to the aggregations, then you will be able to not consider it as malicious afterwards. And so, yeah. And your second question was? I
Domain name parking. So
yeah. Yeah, in that case, we didn't really yet investigate it, but I think, yeah, we may have the case that we have a domain that is really stable until a certain point. So maybe, normally, I think we should be able to see that it changed, but I think we didn't really look at this. I cannot confirm by experimentation that we have done this, but I'm confident we should be able to see, because normally it changes completely behaviors. I think the most problem is this kind of approach, and every kind of approach I try to learn and so on, is this kind of really stealthy attack where we change slightly the behavior, this kind of foreballing attack, which is, I think, very challenging problem.
Thank you, Jeremy. John? Okay. John Levy? Yeah. Yes.
That's okay. I only have 8 slides, so this is going to be a short talk. Yeah, next slide, please. Yeah, spam filtering is an interesting application, because unlike pretty much any other application, you have intelligent adversaries who are trying to break your model. So you know, the filters adapt, the users adapt. Next, please. Spam filtering falls into 2 general categories of things you look at. Part is the metadata, like the connecting IP and who the to and from addresses. That kind of filtering is cheap, so we do it whenever we can. That turns out to get a lot of spam, but it doesn't get all of it. And particularly when you have sources like big commercial mail providers, where most of the users are nice, but they have a constant stream of spammers signing up and sending stuff, you have no alternative but to look at the bodies. And the contents filtering works in a variety of stuff that you look inside it. And it's always relatively expensive, because you actually have to accept the message and then decide what to do with it. Next, please. Originally, we did static filtering looking for naughty words. You know, so we looked for Viagra, but then the bad guys adapted and they spelled Viagra a little differently. So we know how to use regular expressions, and we made the regular expressions ever more exciting. And you know, that third regular expression will actually catch a fair amount of spam of the fake drug variety. So now, in fact, the stuff is dynamic, and we haven't given up on regular expressions. And Spam Assassin, which I'll mention a little more later, they have a whole bunch of regular expression patterns, and about every day or two, they will send you a new set of patterns and weights. Spam Assassin takes all of the stuff that matches, and everything that matches assigns a score, and it adds up the score, and the higher the score, the spammier it is. So it takes all the regular expressions, and then when you download them, then your computer spends 10 minutes compiling them into a big honking state machine, which of course it can now run very fast. And then, you know, so that's sort of machine learning, because they've actually computed the scores by doing regression testing on their spam corpus, but it's not really. So next, please. So about 10 years ago, Paul Graham at MIT did a very MIT thing, which was to say, well, we've never paid any attention to this before, but we're MIT and we're very smart, so we're going to solve the problem right now. And he published a paper called A Plan for Spam, which is easy to find online. And his observation, which was actually pretty smart, was that the words in spam and the words in non-spam are statistically different. So he said, well, you look at the spam and you look at the non-spam, and you make a Bayesian filter on it. So next, please. So you start by tokenizing the message, and different people will tokenize it in different ways. Some look at the headers, some look at the body, some look at both. As we saw from the Viagra example, trying to decide what a word is requires a certain amount of intuition and approximation. But once you've done that, then you make a big database of your words or your word sequences, and you compute scores, and then you do filtering based on the scores. And then when your filters turn out to give you the wrong answer, you go back and tune them, which we'll refer to in a minute. It turns out that one of the things that makes this difficult is that while it is really easy to find databases of spam, because people report their spam all over the place, it is much less easy to find databases of non-spam, because non-spam is by and large people's personal email, which they're not particularly interested to give up to you. So in the early work on this, there was a sequence of conferences called CEAS, Conference on Email and Spam. Barry Leba was the chair of several of them. And we had an endless stream of papers where they were doing some sort of filter tweak tuning, showing how wonderful the filters were, and like they were too corporate that everybody used. Like, it turns out that when Enron collapsed, there was a huge data dump of everybody's email. So the Enron corpus was everybody's non-spam corpus, and so it was given that it was a fixed corpus, it was pretty easy to tune to. And in reality, the results weren't very useful, which is why one of the reasons why that conference doesn't happen anymore. Next, please. So there are various, the typical ways to tune is the first thing you do is you auto-tune. As mail comes by and is characterized as spam or non-spam, you feed that back into the filters to adjust the filters. Most large systems have ways for people to mark misclassified mail. I mean, there's a junk button in your inbox, and there's a not junk button in your spam box. And when you do that, one of the things they do is they go back and they tune their filters. But the filter tuning turns out also to have a lot of iffy stuff. Like, the easiest way to do it is for the entire system to have one shared set of filters, but it turns out that different people's mail is quite different. And at Gmail, for example, every individual Gmail user, all 400 million of them, has a separate set of statistics. And I don't know to what extent that they mix stuff together, because it's all proprietary. But they have assured me that that if you mark something as spam and I mark something as non-spam, it will remember, and it will probably characterize it correctly for us. And then adding to the excitement, there are hostile users. So if you were a spammer and you wanted to send stuff to Gmail and you wanted to get it into boxes, what would you do? What you would do is you would sign up for several thousand Gmail accounts, and you would then send those accounts your spam, and then you would go in through and mark it all non-spam, okay, to try to poison their data. So there are ways to have to deal with that too. Next, please. The first place I would look if I were you is at Spam Assassin. It is a large open source project. It is written in Perl, so it is relatively easy to read, because it's shorter than if it was written in a lower level language. Everybody uses it. It has lots of plugins. It has a fairly sophisticated tuning system built. There's a fairly sophisticated Bayesian system built into it. The only thing that's bad about the Bayesian system is that feeding in the data is your problem. So it will do auto tuning, but Spam Assassin simply is something that sits in the mail stream, and you give it a message and it gives you a score. And if you want to go back and retune the data, there's a separate program called SA Learn that you have to arrange to say this is spam and this is not spam. And different people do it. Different people do it in different ways, some of which are more successful than others. Next, please. So if you look at Spam Assassin, that you'll sort of get the state of the public art in Bayesian filtering. And then there's a couple of more things I'm going to talk about on my. I think this is my last slide. Yeah, my last slide. Another thing that was an idea that was obvious in retrospect a few years ago was Biple's Razor, which is now another SourceForge project, where people would simply send in mail and say this is spam, and they would actually send it. They would send in checksums of it, and they would make databases of the checksums, and then you could send it, and then you could then go look when you were wondering whether a message was spammy. You could send in the checksum, and Razor would tell you, like, yeah, this has been reported as spam, or it hasn't been reported as spam. Now, of course, the spammers attempt to poison that too. So Razor actually has a meta reputation system where where each reporter has a reputation score, and if Razor tells you something that it was spam and it actually wasn't spam, then that will count against the reporter's score. So they have this two-level system where first they look at the reputation of the reporter to decide how seriously to take the report, and then and then they take they fix that into the database. Again, it's open source. It's worth looking at. And then a simpler system, which actually works nearly as well, is the distributed checksum clearinghouse. And what it does is you guys run all your mail through it, and it makes 3 checksums for each message, a sort of a literal checksum, and then 2 checksums that are increasingly fuzzy to try to deal with the variations the spammers put in their mail. And it just counts them. And then you come back and, and it's very high performance, and it deals with hundreds of millions of messages a day. And it will tell you if something looks bulky. And if DCC tells you that something is bulky, that means that people have seen a lot of copies of it. What's wrong with that? Well, like everything the IETF lists send out are bulky. So you need some way to whitelist around DCC. But if you can whitelist around it, this sort of bulk counting, this sort of bulk counting works well. And it's not, it's not exactly machine learning, but certainly the way that the numbers come through and the scores come up and they're passed back and forth and people come up with different opinions of them are sort of like machine learning. And there's an add-on for IP reputation, which goes and feeds back for each IP address how much of its stuff is bulky, and if you can, and that is automatically tuned by feedback, and that gives you an idea of, like, if a message comes in and you're wondering how spammy it is, you can take the reputation to the IP and feed that in. And something that occurred to me since I made this last slide is there are people doing a lot of machine learning on domain names found in mail, and particularly you're looking for domain names that are phishes or that are links to malware and stuff. And I know people who are doing really interesting machine learning stuff with where they'll take the domain names and then they'll try to figure out the interesting characteristics of them, like are they on the same name servers as other domains? Do they have similar whois characteristics? Unfortunately, as far as I can tell, none of that is public. Not so much because it's proprietary for financial reasons, but it's proprietary because they don't want the spammers to know how to circumvent it. But I would look at the Bayesian stuff is definitely machine learning. Some of the bulk counting stuff is machine learning, and some of this domain analysis, which I think overlaps a little bit with the previous talk, is machine learning too. And if you can figure out how to do it better, we sure would like to know about it. So that's it. Do we have any time for a question?
No.
Okay.
Thank you, John. Thanks. We have to take the discussion to the mailing list. Next will be Shufan.
Schenk for the future, this is Lars Eggert. I think it would be useful to not only cram the sessions full of presentations, because one reason to meet face-to-face is to have discussions.
Oh, sure.
Right. So if you can't discuss it, why do we look at it?
Yeah, sure. Sorry about it. Today I take too much time. Yeah, sure. In any case, actually, our IETF and IRTF working on mail list. Mail list is a place always be available for all the time. Yeah. Super.
Okay. So I will give a brief introduction of our attempts on automatic network configuration using machine learning. Okay, as we all know that devices are well organized into the networks. As for each devices, we shall set a set of parameters to make sure that it can cooperate well into the networks without any confliction. Then here is the question coming to our mind. Next, please. That is, will we set up a new networks with several devices, or will we are to add or remove some devices from the network? What problem we shall consider? I think one of the problems is about the parameter setting for each devices. Okay, now let's define the problem. As for the parameters, we have some original parameters for each devices as the input, such as the network topology and device vendor type, etc. And then what's our expected to have for the output? Next, please. For example, we want to get some linking parameters such as the IP addresses, IGP error ID, and IGP cost, etc. Okay. Once we have defined this problem, then what was the traditional way that we use for parameter setting? Next, please. And okay, that's also tells why we shall choose machine learning. I think in this morning, Mr. Jiang has already introduced a lot of why we should choose machine learning. Here, I will only summarize it in 2 points. Firstly, traditionally, we will use the program-aided artificial configuration, which means that mostly the parameters are decided by human. Although with some programs, the limitation is that generally the programs are strictly defined. It is inflexible. It's hard to adapt to the new networks. And secondly, it usually takes human beings days to setting the parameters, although with the helping of the programs. It is generally inefficient and leading to huge cost. However, as for machine learning, it can offer us an automatical configuration. So firstly, it is relatively flexible and universal because we will learn from the existing networks rather than strict pre-rules. And also the machine learning will support incremental learning, which means that the systems can be self-adaptive to the new networks. And later, we have very quick automatic processing. As for our small systems we set up, it only takes minutes to finish the setting of the parameter setting for the whole networks. So it is relatively efficient and low cost. Okay, so actually our project collaborated with Huawei company. Here I will not go to the details of the strategies of our system design. I will only give a brief introduction of the properties of our systems. So firstly, our system can be adaptive to hierarchical layers. It can process the core layer, convergence layer, and access layer. And secondly, it can handle diverse topology, no matter it's star tree, bar string, and etc. It's no problem. And thirdly, the system can not only handle global parameters, but also local parameters. For example, the IP and the IGP address ID are global parameters, while the IGP cost is local parameters. And also the system could handle the local configuration and the global configuration. It can help to set up new networks from the very beginning. And also it can make some local modification while we add and remove some devices. Okay, and here I just use some figures to illustrate how it works. And as for the input, we shall input the network topology to the system. And the next please. And also we shall input the types of the devices, some basic original parameters. For example, here is for the core layer and the convergence layer, and the next slide is for the access layer. Okay, as for output, okay, it can set up the look-back IPs for core and convergence layer. We can see that the IP setting is very similar to the human setting. Okay, and next is for the access layer, also the look-back IP. Okay, next. Besides look-back IP, we can also set the interface IP. Here, for each devices, we may have several interface IP. But here, for illustration, I only show one interface IP here. Okay, next. This is the interface IP for the access layer. Okay, later. And here is the output for the IGP error ID. Is also another global parameter. And the next slide is the IGP cost. This parameter is actually a local parameter. Okay, next. Also show a figure of the local update. Will we adding or remove new devices? For this example, we are to add the new devices. For example, we are to add new devices between two existing devices here. Okay, after insertion, the system will draw the new figure and inserting the new one. And the next, here is the interface IP of the new devices and also the IGP cost of the new devices. Okay, actually I only show some representative figures and examples, not showing all of the parameters. Then I'll give a brief summary of the system. It's relatively flexible because we only learn from existing networks and we only taking the common rules as prior knowledge. We do not set a lot of prior rules. So it's universal and easily adapting to new networks. And secondly, is extensible. During the system design, we consider the modularity to make sure that it can be easily extensible to a future network. And last, we try to balance the global and the local configuration. As we know that some of the parameters emphasize the global properties of the network, while some ones emphasize the local configurations. Okay, so that's all for the introduction of the network. Here, as majoring in data mining, I'd like to share my own experience on machine learning. Okay, so what's the key issue coming to my mind while I do the machine learning project? So the firstly is about the clear problem definition. Because data never tell where to go. Sometimes data can tell a lot. As it can tell a lot, I think it may also tell us nothing if we do not make clear. So we shall firstly set up a very clear learning aim. For example, if we want to see the distribution of the data, or we want to see some hidden patterns of the data, we shall make sure that how the pattern looks like and what information we hope the pattern to deliver. And then we may also want the data to help us to make decisions. So at the first beginning, we shall make the aims clear. And then we shall also make clear how to evaluate our results. We'd better set up a clear evaluation standard at the first beginning. Okay, after problem definition, I think another question is about, do we have adequate representative data? So then how do we define representative data? I think if for our learning data, if the data only covers a small portion of the whole searching space, it may not represent the distribution of the whole searching space. I think it is not very reasonable to use this small portion for the prediction. Okay, so generally we hope that our learning data is randomly distributed over the whole searching space. So random resampling is always preferred. And sometimes we also do the data cleaning. It is necessary to to increase the quality of the data. Okay, so how about adequate? I think it's very hard to analyze adequate. Different algorithms have different requirements on the training data. For example, the neural network requires relatively huge amount of training data. But generally, I think the training samples are expected to be much more than the testing set and the samples to be predicted. Otherwise, the prediction may not be very reasonable. Okay, so after I have adequate data, I'm not feeling very happy, because here comes the most challenging part for machine learning. And to me, I think it's the most challenging part. It's about the feature, it's about the feature selection. Then how can we define proper features? How can we figure out proper features? I think feature definition sometimes can decide whether the project will be success or not. Okay, so besides feature, we also shall define the object. Generally, the features are used to describe the object. For example, as for the network project, we may define the devices, each devices as an object. And we may also define some local topology as the object. I think this depends on the aim of our mining. No, how to say? If they can help to make the prediction better, I think we may try to define the object in multiple dimensions. And then based on the object definition, we shall try to define features to better describe the object. So I'd like to classify the features into two categories. The first is the original features, and the second is artificial features. The original features is very simple, right? And how about the artificial features? It's somewhat like the transformation of the original features based on some common sense or based on some prior domain knowledge. As we know that the machine is not that clever, not as clever as us. The machine will treat most of the features, how to say, similarly. He cannot join correlations. He do not know, okay, which of the features may be strong correlated. Okay, for example, if you define me as an object, okay, you know my height and my weight, then I think for human beings, it's easy for us to know that my figure, right, relatively slimmer or fatter or fit. However, if we put all of the parameters to the machine, he will treat all the features similarly. He may just consider maybe the length of my hair and my weight. He will mix these two features together. So that's terrible. So that's why we called it artificial features. Okay, that's required the machine learning researchers to have how to say very nice cooperation with the domain the domain researchers. Okay, so next one is about the database design. Okay, after we get enough features, I think this is relatively easy. According to our mining step, we shall group the data into different relation tables to make sure that it can facilitate the future processing. Okay, and then later, next one is to figure out the suitable method or algorithms. That is to try out the effective method or algorithms of our problem for the question. However, we all know that there exists no perfect algorithm for all data. Maybe for this kind of data set, this algorithm is relatively better. But if we change the data a little bit, and it's totally different. So sometimes we call it a data-oriented algorithm optimization. However, this may not become a main problem, as we know that big data might decrease the effect of algorithm selection, which means that our algorithm may not be very sensitive to the data. Okay, and finally, it's about the learning result. We shall always figure out the statistically significant results. We all know that machine learning can never deliver absolutely right answer. It only deliver answers of high statistical probability. So if the predictive results are not statistically significant, the machine learning is in vain. That is, the predictive result should be of much higher possibility than the random cases. Okay, so that's all for my sharing. Thank you.
Thank you, Susan. Next, Haiping. Yeah, we have less than 10 minutes left.
Hi, everyone. This is Haibin from Huawei. The slides are from my colleague Zhang Liang. He has been doing research on the network fault analysis with big data. Next slide, please. With this slides, I will introduce our work on the network fault analysis to let people know that machine learning can do a good job in this work. And here is the example scenario of the big data analysis. Our goal is to combine the online and offline analysis to locate the time and the device module and those abnormal events in our customer, for example, operators network or the data centers network. So the online analysis is that we deploying our online system near the customer side. It is used to do real-time detection of the fault and give proper advice to our customers. And the offline analysis is that we have our technical assistance center or global technical assistance center in the backend, and when some fault cannot be diagnosed in the customer side, it can be sent back to our TAC or global TAC, and we can do the offline analysis. So next slide, please. Here is the offline scenario for fault analysis. First, the logging information from the customer side, for example, from the routers, the logging information from the routers or from switches or as transport devices can be uploaded to the global fault diagnosis center. And after that, there will be different mirrors in the TSC to do the fault analysis. We usually have visualization and also visualization. You can see that there is you can see the events and the relationship with the events. That means when one event happens, another event might also happen in the next step. We also do KPI analysis used to detect the traffic anomaly. Here is an example that with the log information, you'll find the traffic decreases sharply at 1720, and there is a command shutdown at that time. And we also do anomaly analysis with a lot of multi-sets data analysis, and we also do correlation analysis. You have to define the which data sets are related to this event, and you must filter those that does not have any relationship with this event. Next slide, please. This is a visualization and makes our customer get insight to the fault, filter unnecessary information. The first picture, you see that the different colors are different, I think, different equipments, and the horizontal axis is the time, and the vertical axis is the traffic. You can monitor what the behaviors of these equipments. And the second picture, here are the events happen in the system, and you can mark the events that you care with different colors, and you can get a rough sense and the correlationship between these events. And we also do, in the last figure, we also do the event analysis with data analysis, which means one event might have relationship with another event, or they have nothing correlation with each other. And we also define the degrees with, I think in the next slide we can see that. No, maybe in the next slide, but I will talk about this first. Okay, go back. The anomaly detection is used to find the possible fault time and the possible device and the possible module. In the first picture, with the we can see at some time there is abnormal traffic behavior happens, so that might be with high probability that might be the start of the fault, and you should check the logging information from that time. And in the second picture, we can see this is the nodes are the routers. We can see that only one router has many more message exchanges with other routers, but among those other routers, they don't have so many routing message exchanges. So so the router in the center of this picture might be the problem, might be the fault device. And last okay, this one. We also do event summarization with visualization. You can summarize the event with the username, with the event name, with the time, with the classification of this event, blah blah, etc. And I want to emphasize the last picture that we have defined degrees for the correlation of different events. That means when what is the possibility of the next event when one event happens. So if it has a high, it can have higher probability to cause the next event happen, or it has low correlation degree with other event, or it can be isolated with other events because they have no correlation with each other. For example, here the event F has nothing to do with other events in this picture. Okay, next slide, please. The time lag is a very key feature for our fault analysis. It is hidden temporal dependencies with sequential data. For example, one event might have some correlationship with another event, but the time lag is within some range. But when the time lag is much more different from that normal range, there might be something wrong there. Okay, next slide. Here in this picture, we also analyze different metrics, KPIs to determine which metric is the cause of the fault. The horizontal axis is the time, and the vertical analysis is axis is the I think it's traffic or it's abnormal behaviors, and the different colors represent the different metrics. So we can easily find which metric is caused. So next slide, please. In this the first picture, it represents the routing, the message exchanges, that is ISRS message exchange between these routers. And we can find that the second router has more routing message exchange with other routers, but we don't have many routing message exchange among those other routers. And in the second picture, we can use algorithms to, for example, use page ranking to determine which one is the hottest one in this picture. So to look at the bad behavior router. Okay, next slide. Okay, thank you very much. That is our work. Any comments? Okay, thank you.
Thank you, Happy. We're already running out of time. 2 minutes past. In any case, we should very much interested in this machine learning applications in the network area. So I do encourage, first, for people to participate in the mailing list, because for IETF we have the meeting every 4 or 5 months. So mail list would be very headway to daily discussing. And I also encourage you guys to apply time slots for the next meeting, maybe in Buenos Aires, then as early as possible, and then I can, according to our RG requests accordingly, maybe get enough time for every presentations. Nas?
Yeah, Lazar, so I encourage you to also consider meeting where the researchers are, where the academics are, so conferences. You shouldn't only meet at the IETF. And,
sure.
My other comment would be that the organizing team, which is you and whoever else is sort of wants to create this group, maybe think about theming the meeting so that you pick a certain topic and you're only going to talk about stuff related to that subtopic at a given meeting, so that's not going all over the place, and leave enough time for discussion.
Okay.
All right.
The points well taken. Thank you. Thank you all you guys. Maybe see you in Buenos Aires, maybe sooner, if we have another meeting. Thank you. Anybody haven't signed the blue sheets, you still have the chance.